Welcome to lecture 8 of the course on high performance computing. We are in the process of trying to understand both how function calls and returns are implemented, as well as how the MIPS-1 machine language instructions can be used to describe various things. So, the function call and return is our first example. In the previous lecture, we had worked out the various steps which must happen as part of function call and as part of return. And the fairly obvious ones were that there must be a transfer of control from the caller to the callee, and at the point of return, when the return has to be done, there must be a transfer of control. Then there were various other issues which came up, such as if parameters have to be passed, then that must explicitly be done. If local variables are present, then space must be allocated for them, and so on. If return value has to be passed, it must explicitly be done, and so on. So, in this series of steps, we found that there was a important data structure which would be involved, and that was the stack. The very same stack that we had talked about when we talked about stack allocation of data. We talked then about stack allocation of data, explicitly the local variables and parameters of functions, which have a lifetime of the call of the function. In other words, the local variable comes into existence when the function is called. It ceases to exist when the function returns. And we now understand how that happens. The local variable comes into existence as part of the function call because there are instructions which explicitly allocate space for those local variables on the stack. And those local variables cease to exist when the function is returned because there are instructions which explicitly free the space that was used for those local variables from the stack. And therefore, the stack allocation of local variables and parameters that we learned about earlier, we now clearly understand is something that is implemented by either by the programmer, if the programmer is implementing this series of steps, or by the compiler, if it is the compiler that is causing instructions which do all this functionality to be included in your program. So, since the stack is the important part of this, we looked at how to implement a stack in memory and saw that in order to push something onto the stack, a 2-instruction sequence was necessary, a subtract or an add depending on whether the stack is going up or down in memory, followed by a store. It would be a store byte if you are pushing a byte onto the stack. It would be a store word if you are pushing a word onto the stack. And as far as the pop is concerned, pop operation, which removes the topmost element from the stack, once again a sequence of 2 instructions, a load and an add to update the stack pointer. In this particular example and in general, we understand that the stack pointer is a very important part of the stack and therefore of the function call return mechanism. And since it is frequently accessed, it would not be beneficial to implement the stack pointer itself as a variable in memory, but rather to dedicate a general purpose register for the stack pointer. And if one is reading programs in assembly language, instead of seeing the general purpose register referred to by its actual name R29, one might, for example, find it referred to by the abbreviation RSP, or as in the case of the assembly language file that we saw earlier, %sp. Right? So, the stack pointer and the stack are very important structures as far as the function call is concerned. Now, let us go back to our example of the function call. We had a situation where there was some program. There was the function which is being called, that is the function b, void b, takes one parameter, has 2 local variables a and b, and this is the point of return. And then there is the function a which calls the function b, function a which calls the function b with a parameter value of 5. So, in the previous lecture I had these functions with function a on top and function b on the bottom. So, here I have chosen to do the other way around. Just note that we refer to a as the caller. Right? In other words, the function call takes place inside the caller function, and we refer to b as the callee. Okay. So, now we understand the series of steps that has to happen, and let us just run through them in terms of the MIPS-1 instructions that could implement that step and the impact that execution of those series of instructions would have on the stack. So, we are going to run through this step by step. Okay. Now, let us suppose that the stack is as shown in the diagram over here. Here I am showing you a slightly different stack from the one that was in our previous example in the previous lecture, because here the stack pointer is pointing at this location, and from the orientation of the stack you would guess that the stack is going to grow in this direction, downward, in other words into higher and higher memory addresses, which is the opposite of what we had with our in the slide we saw just a few seconds ago with the push byte and the pop byte. So this is a stack which is growing into higher and higher memory addresses. Okay, so let's just look at the first series of instructions and try to understand what they are doing. We'll do this the other way around. Rather than saying what series of instructions can implement this function, this operation, let's look at a series of instructions and try to understand how they might be contributing towards the function call and return. So the first instruction that you see here is add immediate, this one, add immediate R1, R0, 5. So what does this instruction do? It's an add immediate instruction. It has an immediate operand of 5. The other operand is R0. R0, you'll remember, is general purpose register 0, which always contains the value 0. Therefore, what this add is doing is it's adding 0 to 5, which is equal to 5, and putting that result into the destination register, which is R1. In other words, all that this first instruction is doing is that it's getting the value 5 into register R1. So R1 now contains the value 5. That's all that this first instruction is doing. Now the second two instructions look vaguely familiar. The add immediate R29, R29, 4 and store word 0, R29, R1. This seems to be a series of instructions which is capable of pushing onto the stack. Remember, as far as pushing is concerned, we expect to see store word or store byte or store half. So what exactly is happening over here? Here the first instruction in the sequence, add immediate R29, R29, 4. R29 is the stack pointer. So this instruction is incrementing the stack pointer by 4. So R29 plus 4 is the new value of R29. What does it mean to increment the stack pointer by 4? Why is it being incremented by 4? In our previous example where we were incrementing the stack pointer or decrementing the stack pointer, we did so by 1 because we were pushing or popping 1 byte onto the stack or from the stack. In this particular example over here, we are dealing with integers, and the assumption seems to be that the size of each integer is 4 bytes, which is why in order to store a word onto the stack, I need to push 4 bytes onto the stack, or I need to increment the stack pointer by 4 bytes. So this explains why add immediate R29, R29 is 4. This is causing the stack pointer to get updated by 4, and then that particular memory location, which is referred to using base displacement addressing mode by displacement of 0 from R29, is where I store the value which is currently stored in R1. What does R1 contain? R1 contains the value 5. So the net effect of these three instructions is to push the value 5 onto the stack. And this is a stack where at any given point in time, the stack pointer points at the current top of stack, which is why when I increment the stack pointer first and then I store into that location. So the stack pointer R29 always points at the current top of stack. So the net effect of these three instructions is that my parameter value 5 gets pushed onto the stack. So the stack pointer which used to point before this sequence of three instructions, the stack pointer was pointing over here. After the sequence of three instructions, 5 has been pushed onto the stack, and this is the stack pointer has been incremented. Therefore, the stack pointer is pointing at this current top of stack. So this is the pushing of the parameter onto the stack. Okay, now you'll recall that this is the passing of the parameter value 5, and that's the only. Other than this, 5 had no special meaning. It just happens to be the value of the parameter in this case. Okay, now after this, the jump transfer of control to the function which is being called, the callee, can take place. And as I have been suggesting all this time, the transfer of control, the implementation of the function call, is going to be done using the jump and link instruction. So in this particular case, I'll use there are two versions of the jump and link instruction, as you'll remember. There's JAL and there's JALR, and they differ only in that jump and link takes its operand in absolute addressing mode, and jump and link register takes its operand out of a register. So in our current situation, remembering that I will use labels to represent memory locations in terms of absolute addressing mode, In order to refer to the transfer of control to the function, I use jump and link B. In other words, execute the jump and link instruction with target address of whatever the address of B is, and B must be referring to the first instruction in the function B. So that's what the label B will be associated with. Okay, so that in fact what we have over here. The first instruction associated with the function B has a label of B associated with it. Okay, now let's just remind ourselves what the jump and link instruction does. Going back to the table of the MIPS1 jump and link instructions, the jump and link instruction, over here the example is jump and link R2, but the example we have is jump and link to the label B, which is similar. Other than instead of copying the value of R2 into the program counter, we are going to copy, or we are going to store the address of B, whatever the label associated, whatever the address associated with the label B, into the program counter. So the second instruction, or the second operation, is what is causing the transfer of control to happen. What is the first instruction doing? The first instruction, as we now understand, is helping us in the remembering of the return address. So it is remembering PC plus 8, which must have something to do with the return address, into register R31. Remember, R31 is an implicit operand of the jump and link instruction. R31 is not mentioned inside the instruction, but it is used by the hardware in implementing the instruction. Therefore, there are these two steps. The second one is the transfer of control to the function which is being called. The first is something to do with the saving of the return address. So the return address is something after the program counter. Remember that the program counter in this particular case will contain the address of the jump and link instruction, and therefore PC plus 8 is one of the instructions following the jump and link instruction. And so that seems to be, we'll talk more about what that 8, where that 8 comes from shortly. But in any event, at this point we understand that the jump and link instruction down here is going to cause control to be transferred to the beginning of function B. Now inside function B, you'll recall, it's important that we remember that return address. Just keeping it in register R31, where it was left by the jump and link instruction, is not going to be safe because of subsequent recursive function calls or nested function calls, etc. Therefore, one of the first things that must be done inside the function, the body of the function B, is to save that return address, as we saw, on the stack. How does one save the return address on the stack? Once again, using the instructions corresponding to push. In this particular case, once again, I increment the stack pointer using add immediate R29, R29-4, and then I store the contents of register R31. And what does R31 contain? For the moment, without fully understanding it, we expect that R31 contains the return address. In other words, the address of the instruction to which control is to be transferred when the return has to happen. That is what R31 contains. Why it is PC plus 8, we do need to understand, but we're postponing that. So the first thing that we do, that we find inside the function call, at the end of inside the function, is a sequence of two instructions which will push the return address onto the stack. As a result of executing those two instructions, what does the stack look like? The stack now looks like this. The stack pointer has gone up by 4, and the thing at the top of the stack is the return address, the address in memory of the point in the instruction, which is where the control is to be transferred on the return. Okay, so now we're ready to actually execute the body of the function. That's what should follow here. But prior to doing that, we have to allocate space for the local variables. In this particular example, I'm not going to include instructions for saving and restoring of registers. But if that did have to be done, then I would have had to save registers prior to the function call and restore the registers just at the appropriate point in time. So in this particular example, we're not looking at the saving and restoring of registers. But we do have to allocate space for the local variables, since function B does have two local variables. If function B didn't have any local variables, this would not have been a step that had to be incorporated. So how do I allocate space for integer A and integer B? In order to do this, I must know how much space integer A and integer B require. Each of these is an integer variable. We are working under the assumption that each integer variable occupies 4 bytes or 32 bits, and therefore the amount of space that has to be allocated is 8 bytes for the integer variable A plus the integer variable B. How do I cause that space to be allocated? Basically, I can do this by just incrementing the stack pointer by 8, which I do by a single instruction, add immediate R29, R29, 8. The stack pointer will then be pointing at the location of local integer variable b, and the space above that is the local integer variable a, above that is the return address, and above that is the parameter which had been pushed onto the stack, which is in fact the integer variable x as far as the function is concerned. So at this point, the body of the function can be executed. And the question which you will ask is, inside the body of the function, it is possible that the variable x is referred to, and the variable a is referred to, and the variable b is referred to. How are these variables going to be, how are the addresses of these variables going to be understood? How is the compiler going to generate the address of each of these variables? Looking at this diagram on the right side of the screen, it's fairly clear how that's going to be done, because we can see right off the bat that in order to refer to the variable b, one just has to refer to the stack pointer with an offset of 0. In other words, 0r29. Inside the body of the function, 0r29 is the address of the variable b. What is the address of the variable a? It's going to be stack pointer, but 4 bytes above, and therefore this is going to be relative to the stack pointer or the base register r29, a displacement of -4. That's what the address of a is going to be. What about the variable x? So this is what I would call -4, this is what I call -8. I realize that the variable x, the parameter in terms of its local name as x, is going to have associated with an address of -12 r29. Therefore, inside the body of the function, if there's any need to refer to x, it will be done so as -12, a displacement of -12 from r29. r29, you'll recall, is the stack pointer, which during the execution of the body of the function is pointing at this location. And just by using this simple picture of what the stack looks like, the compiler can compute the address of any local variable or any parameter. Now, if there are a lot of local variables and a lot of parameters, it could be the case that you have a very large negative offsets and displacements, and therefore the compiler has the option of doing something a little bit different. And in general, the variation would go along the lines of, while the stack pointer is pointing at the top of the stack, the compiler could actually associate with some intermediate location in memory another register, let's say r28. So for example, let's suppose that r28 is made to point at the return address location. The advantage of doing this is that as far as local variables are concerned, and if I'm addressing the local variables as displacements from r28 rather than from r29, then the local variable a will have a displacement of +4, and the local variable b will have a displacement of +8. What about the parameter x? It will have a displacement of -4 relative to r28. So under this convention, all of the parameters, and there could be a large number of parameters, would have negative displacements from this pointer, and all of the local variables would have positive displacements from this pointer. And one could refer to this pointer by some other name. It obviously cannot be referred to as the stack pointer, since by definition the stack pointer always points at the top of the stack, but one could refer to it by some other name, and one name which is often used for it is to refer to it as the frame pointer. So that's something which the compiler could do. But in this particular example, it suffices to just refer to local variable b as 0, displacement of 0 from r29, a as -4, displacement of -4 from r29, and so on. So the compilation of the body of the function will be done by the compiler based on whatever the different statements are, and uses of the variables x, a, and b can therefore be dealt with appropriately. The next interesting point in the execution in our sequence is when we reach the return. So what has to be done at the point of return? Now, one thing which we saw had to be done was the cleaning up of the stack. So we're sort of assuming that we have finished executing the body of the function. We are about to return transfer control back to the point of call inside the caller a, and we just want to clean up the stack. We want to get the stack pointer back to what it should look like as far as return to a is concerned. So what should the stack pointer look like as far as the point in time that it has returned to a? The answer is the picture should be the same as it was when we started this example. In other words, the stack pointer should point at the box labeled ... right at the top. Currently the stack pointer is pointing at the local integer b. I need to make it point at the location way up there. That's going to be a displacement of -4, -8, -12, -16. In other words, to get the stack pointer pointing where I want it to, in other words, in order to implement the cleanup of the stack operation, I need to subtract 16 from the stack pointer. So I have this instruction sub I, subtract immediate, R29, R29, 16. And the purpose of this statement is basically to clean up the stack. So the stack pointer is now pointing back here, and essentially these elements are no longer on the stack. Now I will remind you that there is no subtract immediate instruction in the MIPS1 machine language, but there could well be a subtract immediate instruction inside a MIPS1 assembly language, because it's trivial for the assembler to translate the subtract immediate to an equivalent add immediate with the negative of 16 as the parameter, as the immediate operand. Okay, so at this point we are ready to transfer control back to B. There is no return value to be passed. All that we have to do is to get the return address into a place from which it can be used to do the transfer of control. Now the return address is still actually available in memory. Remember, we have decremented the stack pointer at a point at where it's supposed to be subsequent to the return to the caller, but the return address is available at +8 from the current location of the stack pointer. Therefore, to read the return address, I can look at +8 from what R29 currently points at, and what this instruction does is it reads the return address from 8 R29 using a displacement of 8 from the current value of R29, and loads those 4 bytes, this is a load word instruction, into R31. So I'm going to use R31 to transfer control back to the correct return address. How do I actually do the transfer of control back? I can do that using the jump register instruction. I'll remind you that there are 2 kinds of unconditional control transfer instructions in the MIPS instruction set. There's a jump instruction and the jump register instruction. In this particular situation, the jump register instruction is more useful because I have the target address available in a register. Jump register will allow me to transfer control back to an address which is specified in a register. And the result of this instruction is that control gets transferred to PC +8, which is the value that had been stored inside R31 by the jump and link instruction. So that implements the complete sequence that we were looking for. And as I said, we have left out some of the complexities of some function calls, like the need for returning a value or for saving and restoring registers. But otherwise, we have pretty much understood what instructions would be involved and how the stack is involved in what we now see as a somewhat complicated function call and return operation. Okay, now just going back a few lectures, you'll recall that I had mentioned that in CISC instruction sets, it is possible to have single instructions which are somewhat complicated. And it's conceivable that in some of the CISC instruction sets, the entire functionality that we see over here could have been implemented in 1 or 2 instructions. Over here you'll notice that the sequence is more than 10 instructions. Each of those 1 or 2 instructions in the CISC instruction set would clearly be much more complex than the simple instructions that we have in our RISC instruction set. The most complicated instruction that we have in this RISC instruction set is the jump and link instruction, which does 2 primitive operations. Every other instruction just does 1 primitive operation. So much for the function call and return. Okay, now with this in mind, we can go back to our picture from the very first lecture, where we talked about how different variables differ in their lifetimes and how some variables are statically allocated. Some data is statically allocated in memory, other data is stack allocated in memory, and other data is heap allocated in memory. We can now put all of these thoughts together into a description of how main memory is used by a program. When you write a program and you run it on a computer, how is main memory used? Remember, we use the term main memory to refer to that box inside the computer organization block diagram, because the word memory is overloaded. There are registers themselves are a form of memory, and so on. Okay. Now, one very important thing which must be present in main memory for a program to be executed is the program itself. And from now on, in talking about the program itself, bearing in mind that the program itself contains both instructions and data, I'll talk about the instructions of the program using words like code or even text. You'll often find the word text or code used to refer to the region or to refer to the instructions of a program. Right, so very clearly, when a program is executing, its code or text must be present in memory. In addition to this, what must be present in memory is the different data that is used by the program. And some of that data could be stack allocated, some of it could be heap allocated, some of it could be statically allocated. We've seen something about how static allocation is done. When did we see this? We saw this when we looked at the example of the file program.s. You remember that we had in connection with, I'm sorry, not integer but float. In that particular program there was a floating point array of size 100, and we saw that the way that static allocation was done in the assembly language program, associated with the label A, there was a space, in other words an allocation of 400 bytes, which is the amount of space occupied by 100 floats. Each float is a 4 byte IEEE 754 floating point value. So we saw how static allocation is done. Corresponding to static allocation, we will see space directives inside the assembly language program. We've also now seen how stack allocation is done. We saw that the function parameters and local variables are allocated space when the function is called, and that space is subsequently reclaimed on function return, and that the stack allocation is done explicitly by instructions which have been included into the program for that purpose by the compiler. So the net effect is that if I wanted to draw a diagram which shows me what all is in memory when a program is executing, the diagram would look something like this. First and most important is probably the text or code of the corresponding to the program, that is the instructions of the program. This would typically occupy the low memory addresses associated with the program, so memory address 0, etc. Now one thing you should bear in mind in thinking about the MIPS instructions, each MIPS instruction is of size 4 bytes. I mentioned that each MIPS, just like each MIPS register, each MIPS instruction is of size 32 bits or 4 bytes. This was confirmed when we looked at the 3 instruction formats, the I format, the R format, and the F format in the end of the lecture 6. So since each MIPS instruction is of size 32 bits, that means that if the first instruction is at a byte address 0, then the second instruction is going to be at byte address 4. In other words, as far as the text segment, as far as the instructions are concerned, each instruction is of size 32 bits, and the instruction addresses are going to be multiples of 4. If the first instruction starts at address 0, all subsequent addresses are going to be multiples of 4. Okay, now this actually is interesting and answers one question which may have come into some of your minds when in connection with the jump instruction. When we talked about the jump instruction, you will recall that the jump instruction has a 26-bit absolute operand, and this is the target address. In our notation, we actually use a label, but in general, when the machine language instruction equivalent, for example, we talked about jump to B, let's say. B is a label in the program, but that's at the assembly language version. In the machine language version, that would be translated into a 26-bit absolute address. Now, this is only a 26-bit address, but the PC is a 32-bit register, which means that the actual target address must be a 32-bit entity. And in the table on the jump instruction, we had actually seen that the way that the 26-bit absolute address is translated into a 32-bit address is that the 26 bits, which are target 26, are included along with 2 least significant zeros, which adds up to a total of 28 bits. 4 more bits are still needed. The remaining 4 bits are taken from the most significant bits of the program counter. In other words, PC bits 28 to 31. Now, the reason I mention this now is that we understand where the 0, 0 are added as the least significant bits as far as converting the 26-bit target address into a 32-bit actual address. The 2 zeros make sense because any MIPS 1 instruction is going to have least significant bits of 0, 0 in terms of its address. Given that all MIPS instructions are 32 bits in size and that their addresses are multiples of 4, a multiple of 4 has the property that its least significant 2 bits are 0. Therefore, we understand where the 0, 0 are coming from. That's just a fallout of the fact that all MIPS instructions are of size 32 bits and the text of your program is going to be loaded from address 0, which means that all the instructions are going to have addresses which are multiples of 4. What about the other end of the target generation, target address generation? Why does it make sense to use the most significant bits from the program counter value? You'll recall that our interpretation of using bits from the program counter value are: the program counter is the register which contains the address of the current instruction being executed. At this point in time, we are talking about the jump instruction. Therefore, the most significant 4 bits we are referring to are the most significant 4 bits of the address of the jump instruction. Now, by copying those 4 bits into the or by using those 4 bits in the generation of the target address, what we are essentially saying is that the jump instruction and its target differ in only 28 bits, and therefore the maximum distance from which from the jump that the target could actually be is about 2 power 28 bytes, which is equal to about 2 power 26 instructions. Remember that each MIPS instruction occupies 4 bytes. Right? So, what does this mean? This tells us that as far as the actual distance between the jump instruction and its target, the number of instructions that could lie between them could be as much as 2 power 26. How much is 2 power 26? You'll remember that 2 power 20 is approximately 1 million, and therefore the number that we have over here is significantly more than 1 million instructions. It's 2 power 6 multiplied by 1 million instructions, which is tens of millions of instructions, which is conceivably unlikely to be the case for the programs that we write. It will have to be an extremely large program made up of 1 million instructions before this problem kicks in, that the 26-bit target is not adequate to represent the number of instructions, the distance between the target and the jump instruction. Right. So, going back to the diagram, the data, the stack and the heap, the data is this is the statically allocated variables, the stack is the stack allocated variables, and we understand that the stack will grow and shrink with function calls and returns, and the heap similarly may have to grow and shrink depending on how dynamically allocated variables are created and freed. Okay, now as far as stack allocated variables are concerned, let me just recap. The space for stack allocated variables such as function calls, function parameters, function local variables, this is allocated on function call and reclaimed on return. And as we also saw, the variables themselves, the addresses are calculated and used by the compiler relative either to the top of stack pointer or some other base register such as the frame pointer that I referred to earlier in this lecture. Therefore, the addresses of these stack allocated variables are computed and used by the compiler based on the picture that we had of the stack. Right? The compiler knows what the contents of the stack are, since the compiler is in charge of generating the instructions which are going to cause those items to be pushed or popped from the stack. Right? So, in some sense, one could summarize stack allocated variables by saying that the growth of the stack, the growth and the shrinkage and growth of the stack area is managed by the program as generated by the compiler. If you're writing your own assembly language program, it would be under your direct control. If you're writing a C language program, you have no idea that this activity is happening. The instructions to do this are generated by the compiler. Okay, now what about heap allocated variables? Now I had mentioned that heap allocated variables are the variables, the pieces of data whose lifetime starts from an explicit creation point and the lifetime ends at an explicit reclamation point or freeing point, and that this is done in C programs by a memory allocation library. Right? We know that there are functions like malloc, realloc and free. Malloc is used to allocate a dynamic variable. Now, I'm now telling you that these functions are actually members of a memory allocation library. So, just like there was a math library, there's a memory allocation library. So, somewhere there is going to be a .o file which is going to get linked into your program, as a result of which the instructions of the memory allocation library get executed when there is a call from your program to do an malloc. Once again, a series of instructions are going to get executed through which the dynamic allocation of space in memory happens. And the implementation of that allocation is done by the memory allocation library. So somebody writes this library, the functions of this library, such as malloc, realloc, and free, and makes them available to you, and you get the compiled version inside an object file such as malloc.o. Okay, now if your program uses such functions, then this, just like the math library, the memory allocation library will get linked to your program, and will therefore those functions will be available when your program executes, right? Just like any other functions. So these are functions just like any other functions. So just like the function call and return that we talked about, or the function call and return operations that we talked about would happen in connection with the malloc, realloc, and free. They are just functions in a library which are called by your program when it does a heap allocation. Okay, so what about the growth of the heap area? What you're being told now is the memory allocation library is written to allocate space out of memory on requests for malloc, realloc, free, etc. But how is the allocation of that memory actually done? We saw that the compiler does the allocation of stack allocated space. In the case of heap allocated variables, this is obviously managed by the library functions. There may be situations where it needs more memory to be associated with it, in which case it would get the additional space allocated to it and then proceed. And we will be able to talk more about that only after a few more lectures. But for the moment, it's clear that for programs which do use a lot of dynamic variables, these functions and their implementation could be crucial to the performance of the function. Therefore, one could conceivably even think of writing one's own version of these functions if one is uncertain about the quality of the functions that are available by default. Basically in courses on data structures, one might learn simple ideas about how to write functions of these kinds. Okay, now with this, we have seen a simple example of writing MIPS code. We will see more examples of dealing with MIPS instructions as and when the need arises. And where necessary, I will revert back to the table of instructions so that the meaning of each instruction and the form that it takes will be quite clear. Okay, now we need to move on to our next important topic of discussion, which is to actually learn more about, actually before I proceed, let me just remind you that at this point we've seen a lot about main memory. We have seen a lot about the CPU in the sense of we know now what the different kinds of instructions and the different kinds of addressing modes that the CPU has to deal with are, and we understand pretty fully what the registers are, that there are special registers like the program counter or the instruction register, and there are general purpose registers, and that basically the execution of the instructions is managed by the control. We have not seen anything about the MMU or the cache yet, but we will do so shortly. Okay. Now we are going to now move into a stage where we concentrate on the functioning of the processor. We want to understand what happens when an instruction is executed. We know what happens when a program is executed. We talked about how when a program is executed, the program is present in main memory, and the instructions of the program one by one get executed inside the processor. So we're now at that level where we want to understand, we'll understand more about what happens when a program executes. The basic step in the execution of a program is the execution of a single instruction, which is our next target. We want to understand what happens when a single instruction executes. So what are the steps in processing a single instruction? Our base assumption is that to start off with, the instruction is present in main memory, and that to be executed, the instruction must be present inside the processor, because it is the processor that has the hardware to execute an instruction. The main memory just has the capability of remembering things. Therefore, as far as the steps in instruction processing are concerned, the first step must be to get a copy of the instruction from main memory into the processor. And a word which is typically used to describe that operation is the word fetch. So one talks about fetching an instruction from main memory into the CPU. So that's the first step. Now, once the instruction has been fetched from the CPU into memory, it can be processed, because the instruction will be present inside the instruction register, which is one of the special purpose registers inside the CPU. and therefore the control hardware can examine that instruction and start processing it. But how does it process the instruction? We've seen that the instruction will be in a well-defined format, right? So it's possible that the first instruction is a jump register instruction, in which case we know that it is in, let's say, the I format. So how does the processor hardware process the instruction from this point on? Now the first thing that the processor hardware must do is, given that the instruction is present in the instruction register, it must understand the instruction. And typically the name that is given for this step of processing of the instruction is to use the word decode. You will remember that the instruction is present in memory in the binary form, and some of the bits of the instruction contain information about what the instruction is supposed to do. Other bits in the instruction contain information about what the different operands are. In the case of the MIPS1 R format, the information about what the operation of the instruction is contained in some of the most significant bits, which was the opcode field, as well as some of the least significant bits, which was the function field. Therefore, all of that information together will be necessary to decode the instruction. Therefore, while the instruction is sitting in the instruction register, the hardware must examine the appropriate bits of the instruction in order to understand what the instruction is supposed to do, using the information about the instruction format. In other words, what bits of the instruction are used for what purpose. Once this has been done, the instruction can be executed. In other words, the operation that is required of this instruction can be done. And the term which is given for that is to talk about the instruction being executed, doing whatever the required operation associated with that instruction is. Once this has been done, the result of the instruction can be written. So this will be referred to as write. Typically, for many instructions, the completion of the instruction will involve writing a value into a destination register, hence the name of this particular step as write. Now we could look at the sub-steps involved in each of these main steps. There are these four main steps: fetch, decode, execute, and write. Now what are the sub-steps? As far as fetch is concerned, it's fairly clear that in order to get the instruction out of memory, the processor must give memory, must identify to memory which instruction it is interested in. The processor keeps track of which instruction it is interested in its special purpose register called the program counter. Therefore, the way to look at the first step of instruction execution is that the processor sends the value inside the program counter to the main memory. The main memory, on receiving that information, looks up in its memory and returns the instruction at that particular memory location to the processor. The processor then takes the instruction that it got from memory and puts it into the instruction register. So the steps involved in fetching the instruction from main memory to the processor we can now think of as the processor sends the program counter value to memory, memory sends back the instruction to the processor puts the instruction into the instruction register, and then this additional step increments the program counter. Now let's just think of the situation where the second step is not there. What would happen? The program counter, unless there was a control transfer instruction, the program counter would remain unchanged. In other words, the same instruction would get fetched over and over again and executed over and over again. Very clearly, since the default mode of execution is for the processor to finish executing one instruction, and if it is not a control transfer instruction, to then go on to the next instruction, there is a need to automatically increment the program counter as part of instruction execution. And in this particular description of instruction execution, instruction processing, I am talking about incrementing the program counter at the step of incrementing the program counter as happening inside the first step of instruction processing. In other words, I am choosing to describe increment program counter as an operation that happens during the fetching of an instruction. So if the program counter value which was sent to memory was 100, then after incrementing the program counter, bearing in mind that each instruction is of size 4 bytes, the value should now be 104. Therefore, when we talk about incrementing the program counter, what we actually mean is incrementing by 4, since the MIPS1 is byte addressable and the size of each instruction is 4 bytes. So we fully understand what the first step in processing an instruction is, the step which we call fetch instruction. Okay, what's involved in decoding the instruction, the next step? Now, As I had mentioned, decoding the instruction involves the hardware inside the processor examining the instruction, the various bits of the instruction as it resides in the instruction register, with the purpose of understanding what the instruction is in terms of what the operation is supposed to be, what the different operands are, what addressing modes are used, etc. Now, before the instruction can actually be operated, its operands must be available, and I haven't shown that as an explicit separate step inside this 4-step sequence. Therefore, that must be the second basic operation that happens as part of decoding the instruction, getting the operands wherever they may be. Now, in the case of the MIPS1 instruction set, we know that the operands could be in registers, in which case they can be general purpose registers or the instruction register, in which case they could immediately be obtained within the processor itself. If, on the other hand, the operands are to be obtained from memory, as is the case with the load and store instructions, remember, in the MIPS1 instruction set, the only instructions which take operands out of memory are the load and store instructions, and the load and store instructions take their operands in a base displacement addressing mode, for which certain calculation has to be done in order to calculate the address of the memory operand. Basically, for example, if there was a base displacement addressing mode, as we have just seen, -4 from R29, then in order to find out what this actually means, the hardware has to look at the contents of R29. R29 might contain the value 1000, and then it has to add to it this displacement, -4. Therefore, it calculates the value of the operand as 996. So that's why there's an explicit step which is called calculating the memory address. For certain addressing modes, there is a need to do some arithmetic in order to find out what the memory address is. In the case of the MIPS1 instruction set, this is the case for the base displacement addressing mode. For more complicated instruction sets, you'll recall there are addressing modes where different kinds of arithmetic may have to be done, such as the indexed addressing mode, where the contents of 2 registers have to be added, or the post or pre auto increment addressing modes, where a constant may have to be added to a register as a side effect of the operand calculation of the memory address. But in general, in order to get the operands to the instruction, it's possible that some calculation has to be done first, as in our MIPS1 example of base displacement addressing mode. So I'm including 2 basic operations as far as fetch is concerned, that is, getting the instruction from memory into the instruction register and incrementing the program counter. I'm including 2 basic operations as far as decode the instruction is concerned, understanding the instruction as well as calculating memory operands and fetching operands. What is involved in executing the required operation? Well, this will depend on what the operation is. You'll note that if it's an add instruction, then the add functionality in the ALU will have to be activated. If it's a multiply instruction, the multiplier will have to be activated. If it's a control transfer instruction, something else will have to be done. If it's a load or a store instruction, memory will have to be involved in doing the required operation. So the step of doing the required operation will depend a lot on what the instruction is, and on a case-by-case basis, the hardware would have to do the appropriate, initiate the appropriate activity. But the net effect will be that the instruction will get executed, or it's whatever the instruction had, whatever the intent of the instruction was, will have to be achieved. Finally, once the instruction, that operation has been completed, the results of the execution of the instruction can be committed, can be written. For example, if the instruction was add R1, R2, R3, then as part of execute, the value inside R2 and the value inside R3 would have been added, yielding a result which is what will be stored into R1 in the write the result of the instruction stage. So we need to flesh this out a little bit more. So the steps in instruction execution we can now talk about as follows: fetching the instruction from memory to processor, decoding the instruction and getting its operands, executing the operation and writing back the result, which we explicitly write down as fetching the instruction involves 2 operations. One is sending the program counter value to memory. Memory will respond by looking up what the current contents of that memory location are, sending it back to the processor, which stores that instruction into the instruction register. In addition, the processor will increment the program counter which is the same as far as the MIPS1 instruction set is concerned, the same as PC equals PC plus 4. Decoding the instruction and getting its operands involves decoding, calculating the address of the operands, getting the operands either from registers or from memory into the ALU. They are required inside the ALU, since it is within the ALU that the instruction functionality is implemented in hardware. What does executing the operation involve? It involves triggering the appropriate functional hardware. And if it is a load or store instruction, it involves triggering an operation at memory, in the main memory. Finally, writing back the result will typically involve updating a destination register or memory. So this is just a slightly more systematic description of the operations as we had described them. I do want to comment on just one thing before closing this lecture, and that is the fact that we have assumed that the incrementing of the program counter by 4, as would happen in the case of the MIPS1 instruction set, happens as part of the first step in instruction processing is interesting, because this now gives us a little bit of an idea about the description of some of the instructions in terms of the meaning of the instruction in the tables that we saw. And if you look back at the meaning of some of the instructions where there was some doubt as to why PC was not used, but rather PC plus 4 was used or PC plus 8 was used, we now understand that at the time that the instruction is being executed, if one wants to refer to the address of the instruction, one should understand that subsequent to incrementing the program counter, the address of the instruction itself will be PC minus 4, because the program counter would have been incremented by 4 before the instruction itself is executed. And therefore, the address of the instruction which is currently being executed will actually be PC minus 4. And therefore, in looking back at the table that I am referring to, the table of meanings of the different instructions in this slide, a little bit more idea about what is actually happening will arise. Of course, we are still not too sure what the PC plus 8 as far as the jump and link instruction is concerned. You'll recall that in the jump and link instruction, the value PC plus 8 gets stored into R31, which is still a little bit of a mystery. So we'll have to wait for a little while before we understand this. So at this point, we understand the steps involved in instruction execution. And in the next lecture, we'll proceed to look at how those steps would actually get implemented in terms of very simple hardware, and the implications of that very simple hardware on the amount of time that it would take to execute any one instruction of a processor which implements something like the MIPS1 instruction set. Thank you.